Hi there and welcome to today's lesson, grade 11 physical science. And in today's lesson, we're going to be doing Newton's laws of motion. We're just going to start with an introduction to get you familiar, a lot of the concepts you might have heard of before, a lot of the terminology, but we're going to bring it all together so that next time we meet, we can go on to the laws in detail. So today it's a summary, it's an overview, just to get you familiar with it. So let's get going. First thing I'm going to do. Terminology. We need to know what the words mean. We need to know how to use the words. So I've got 4 terms for you. They are at rest, uniform motion, net force, and free body diagram. So I'm going to give you 2 minutes to just jot down, or you can chat to a friend and write down what you think at rest means, uniform motion, net force, and free body diagram. So you've got 2 minutes to write that down, starting now. Okay, so you've had your 2 minutes. Let's have a look at what these terms mean. At rest. Anybody got an idea of what at rest means? At rest means it's not moving. Good. So let's pick a color. Sorry, gents, we're going with pink today. But at rest means that the object is not moving. Okay? What about uniform motion? When people look at uniform, they think, oh, it's the thing that we wear to school. Same idea, uniform means the same. And when we talk about uniform motion, what we actually mean is constant velocity. So uniform motion means that the object is moving the same way all the time, and it is not speeding up. So uniform motion is going to be constant velocity. Now, net force, what is that? You've learnt about forces in grade 9. You learnt about it briefly. You should have been introduced to forces earlier on when we did friction. So net force is the sum of all the forces acting on a body. And that will result in a movement, or sometimes it results in no movement. Okay, so net force is the sum of all forces acting on a body. I think my handwriting is getting too big for this page. Okay, last one, free body diagram. If I can get Some space? Okay, I'm not going to get some space on this. Free body diagram, remember, it is the forces that are applied to an object, that act on an object. When we draw a free body diagram, what we do is we draw a dot, and with that we will draw all the forces. So it could be the normal force. It's a capital with a subscript. Remember, subscript's a little letter at the bottom. And you could have gravity, which will have capital and a little letter going down. Okay, so a free body diagram, remember, the only way that we represent the object is by using a little dot, and it's all the forces that act on a body. So hopefully everybody's with me. We can go on to the more entertaining and interesting things. So I'm going to start with a few questions for you to think about. Don't need you to answer this right now, but I just want you to think. What is the relationship between force and motion? Okay, so another word for motion could be movement. So what is the relationship between force and movement? Okay, so I want you to be thinking about that while we talk about the rest of the things that are on the screen. So scenario one, I want you to picture this. There's a plant on a table, and the table is covered with a cloth. And we've got a nice picture here with a plant on the table, and we've got the tablecloth covering it. So look at these three questions. Is the plant moving? Are there any forces acting on the plant? And what is the net force acting on the plant? So what I want you to do is take 2 minutes again now, and I want you to answer those three questions. Is the plant moving? Are there any forces acting on the plant? And what is the net force acting on the plant? So 2 minutes starting now. Okay, everybody, so that's 2 minutes. Hopefully you've got an answer. Everybody pay attention. Let's see if we can answer these questions together. Is the plant moving? You should have one word. The answer is no, the plant is not moving. Okay? Now, are there any forces acting on the plant? Hopefully you've said yes. And what I'm going to do is I'm going to draw a force diagram. So remember we said a force diagram, draw dots to represent the object, and then we draw the forces from there. So are there any forces acting on the plant? And hopefully you're saying to me that yes, one is the force due to gravity, and that is acting down. And if you remember from friction, there's another force that we talk about, and that force will be acting up. it is known as the normal force, or in this case, it is the table pushing back on the plant. Okay, so there's two forces here, force due to gravity and the normal force. And that leads us on to our third question. What is the net force acting on the plant? So if you've been thinking with each question, is the plant moving? No. Are there any forces acting on the plant? Yes, but they are two forces and they look like they're of equal magnitude, so equal size. So that means that there is a zero net force acting on the plant. And we say there's a zero net force because the plant is not moving. It's not the only time you get a zero net force, but for the picture we've just seen, there is a zero net force, plant is not moving. Okay, hopefully everybody's all right with that. Let's move on and see what else we've got in store. Now we've got one where there is movement. So let's have a look at what I've got for you. Again, the question, what is the relationship between force and motion? And remember we said that motion, another word for motion was movement. Okay, so what is the relationship between force and movement here? And this is the scenario that we've got. So you have a white billiard ball or a white snooker ball moving across a billiard table towards the red ball. So we've got the white ball moving to the red ball. Okay. Questions again. Is the white ball moving at constant velocity, or is it speeding up, or is it slowing down? And then, are there any forces acting on the white ball? And then our third question, what is the net force acting on the white ball? Okay, so again, I'm going to give you 2 minutes. You're going to tell me, is the ball moving at constant velocity, speeding up, slowing down? Are there any forces? And then what is the net force? So again, 2 minutes starting now. Okay, so your 2 minutes is up. Let's see what you've got for an answer. This one you might think is a little bit tricky, but we'll see if we can work through the answers easily. So the first one, is the white ball moving at constant velocity, or is it speeding up, or is it slowing down? Hopefully your brain is saying, hang on a minute, there should be friction here. And I hope your brain has said that, because that means that you've been thinking. Yes, there will be a little bit of friction, but the reason that we chose billiard ball or a snooker ball is because the friction is going to be really, really small. So in this case, Because the friction is small and the surface of the snooker or the billiards table is not going to cause too much friction, we're going to say that in this case, it is going to be a constant velocity because the surface of the ball is smooth. Okay? So then, are there any forces acting on the white ball? So your answer, again, should be yes. But I think where some of you are going to disagree with me, and you're going to say, no, but the teacher's wrong, is these are the two forces that I can think of. I'm going to have force due to gravity acting down, and I'm going to have the normal force, or the force of the table, acting up. Let's just fix our arrow there. But I'm not going to have any force to the left or to the right. And the reason I don't have any force to the left or to the right is because of our last question. What is the net force acting on the white ball? And again, our net force is going to be a zero net force. And if we want to know why, the reason is because we said there is a constant velocity. So if there's a constant velocity, that means that we have a zero net force. Those two concepts go together. So what does that mean? How do we explain that? So we have this terminology, we have this thing here called equilibrium. And what that means is that the forces are in balance. Okay, I'm going to put this in inverted commas because it's not the nicest word to use, but it's just to help us explain at the moment. The forces are balanced, and that means in terms of science that there is no net force. Okay, so equilibrium is where there is no net force, and the forces we can say are balanced. Okay, hopefully you're still with me. We're going to do last bit, and then I'm going to send you off on a break. So, what would Newton say about scenario 1 and scenario 2? So scenario 1 was where we had a plant on a table covered with a cloth, and scenario 2, we have a white billiard ball moving across the table towards the red billiard ball. So what would Newton say about them? Newton would say that there is, in both cases, no net force, but in this case, there is still movement, or there is still motion, okay? Even though there's still motion, he's still going to say that there is no net force. So how do we explain that? And that brings us on to the first of Newton's laws. Newton's first law of motion says a body, or you can say an object, if you don't like the word body, an object will remain at rest, so remember it's not moving, or continue to move in a straight line at constant velocity unless it experiences an external force. So when there is rest, not moving, constant velocity, it's going at the same speed the whole time, and there is no net force, you're going to be experiencing Newton's first law of motion. So when it says experiences an external force, that means that there is no net force. When we have a net force, we are going to have constant velocity, or we are going to have an object at rest. So I'm going to say here that net force is going to be constant velocity, or the object is at rest. Okay, guys and girls, I think you've done really well. We did quite a lot of work. We did terminology. We did Newton's first law. It left you with a lot to think about. So what we're going to do is we're going to go off on an ad break now. You get a chance to just give your brain a little bit of a rest, breathe, and we'll be back with you soon. See you now. Welcome back, everybody. Hopefully your brain had a little bit of a rest, but you've been able to just breathe a little bit. And now we can focus on Newton's laws again. So at the end of the last segment, we spoke about Newton's first law, where we said that an object or a body will remain at rest, remember, not moving, or continue at a constant velocity unless acted upon by an external force. So those were the words that we used. So what I've got for you now is a few questions on Newton's first law. So let's have a look at the screen and see if we can answer these. We're back to our table with a plant on it. And the first question is, what would happen to the plant if someone gently pulled the pink, oh, I can't speak properly, someone gently pulled the pink cloth? And then the second question is, what would happen to the plant if someone quickly jerked the pink cloth? So I'm not going to give you too long. This time I'm really only going to give you a minute. Quickly, with your friend, what are the answers to the two questions? If you pull it slowly, what's going to happen? If you pull it quickly, what's going to happen? You've got 1 minute, starting now. Okay, so I can see that a few of you are thinking, this teacher's gone mad. Why is she asking us such easy questions? The reason I'm asking you such easy questions is because this shows us Newton's laws. And lots of things around us in our everyday life shows us Newton's laws. And that is what is so cool about science, is that you think it's all this amazing, super complicated stuff, and actually most of the time it's really, really easy things that we can see around the house. And this is exactly an example of that. If you pull the cloth slowly along the table, what is going to happen to the plant? Hopefully you've said that the plant, and if I have my pen, that would work, the plant is going to move with the cloth. Okay? Now, if some of you have done what I did when I was young and I tried to cause mischief in the house, and I went and I grabbed the tablecloth quickly because I saw somebody do a magic trick on TV, and then I ended up breaking the plates and I got into trouble, that's because I didn't pull the cloth quickly enough. I pulled it too slowly, so the plates came with it. But if I pull the cloth really quickly, what's going to happen? The plant is going to stay where it is. The cloth is going to move out from under it. So your second question is that the plant stays still and the cloth moves. Okay, that is not permission to go and try this at home tonight and break all of your mom's nice plates. You're just going to have to believe me for this one, because I don't think your mom will be very happy if you break all of her plates. Okay. Oh dear, so I wrote on the wrong one. But here we can see, so what did we say? It stays. And here it says that the plant and the cloth moves. And here, this is going to say it stays on the cloth while the cloth moves. Okay, good. So I know you guys are all there. You're not going to go and try this at home. Next one, we're back. This one, I'm sure somebody is going to try because we're talking about snooker or billiards, and everyone likes to play that at some time in their life. So let's have a look. White ball moving across the billiard table towards the red ball. There we go. So now, these questions. How can the white ball suddenly change direction? How can the white ball suddenly speed up? How can the white ball suddenly slow down? Okay, so I'm not going to get you to answer these questions. I just want you to think. How can it suddenly change direction? How can it suddenly speed up? How can it suddenly slow down? Hopefully you're saying to me, but ma'am, it's not going to do that on its own. It needs something to help it do that. It needs something to make it do that. And that is the perfect answer. That is the correct answer. But now let's look at what Newton says. Okay, what did Newton say? What would he say? What would he say if the white ball suddenly changed direction? What do you think he'd say? What would he say if the white ball suddenly increased speed? What would he say if the white ball suddenly slowed down? Okay, I want you to think about Newton's first law that we did a few minutes ago. Newton's first law said that the object is going to stay doing what it's doing. So if it's at rest, it's going to stay at rest. If it's constant velocity, it's going to stay at constant velocity. Unless, and this is the key part here, external force. And another way of describing external force is a net force, okay, that is greater than 0. What is Newton going to say about these three options? If it suddenly changes direction, suddenly increases speed, or suddenly slows down, Newton's going to say what? He's going to say that there was an external force that was acting. Okay, so you can see we've used Newton's first law to explain why things stay where they are, or to explain why things are moving at constant velocity. But we can also use Newton's first law to go into the second law that he described, which explains why things change direction, why do they speed up, why do they slow down, why do they change shape. And that is now known as Newton's second law of motion. And Newton's second law of motion says the following. A net force, so here this is important, net force will cause a body to accelerate. Now we don't have uniform motion anymore. It will cause a body to accelerate in the same direction as the net force. And the acceleration is going to be directly proportional to the net force and inversely proportional to the mass of the object. So let's have a look quickly. What are the things that we're talking about here? So we're talking about F net. We're going to have a net force. In Newton's first law, he spoke about it as an external force. What are we going to have? We're going to have acceleration. Earlier on, we were speaking about constant or uniform velocity. Now we're talking about acceleration. What else do we have? We're talking about mass. So in Newton's second law, he's taking three concepts. He's taking a net force, he's taking the concept of acceleration, which is a constant increase in velocity, constant increase in the speed that it's going, and the concept of mass, how much substance there is in an object, and he's put those three things together to explain why an object will change direction, change speed, slow down, speed, those sort of things. Okay? Hopefully everybody's with me. We'll go on to Newton's third law in a second, but I want to look at this picture before we go on to Newton's third law, before we go on to a break. We spoke about Newton's second law when we had the billiard balls, we had the objects moving. We can still talk about Newton's second law when an object is standing still, because you're going to have a zero acceleration. Okay, so you need to be able to explain why an object is standing still or why an object is moving using all of Newton's laws, Newton 1, Newton 2, and Newton 3, when we get to Newton 3. So just because an object is standing still does not mean you can't explain it using Newton's second law of motion, where it says that an object will accelerate if there's a net force. So if our net force is 0 because the object is standing still, we can then say that there is no acceleration, so therefore Newton's second law does not apply. Okay? Again, a whole lot of things that you need to think about. Force, mass, acceleration. Okay? We've had a much shorter time to think about these things now. I'm going to give you one more ad break, then we're going to push on to the end. So I'll see you soon. Okay, welcome back. So we've had quite an intense first session before we went to ad break, and the second one was quite short. So before we go on to Newton 3, I just want to make sure that everybody is with me in terms of Newton's second law. So I'm going to go over Newton's second law again. Then I'm going to show you the equation that comes with it, because we're going to spend a lot of time in the next few lessons using Newton's second law equation. I want to make sure that you know exactly what's going on. So let's look at the law again. And then we'll talk about the equation. So Newton's second law, a net force causes a body to accelerate in the same direction as the net force. The acceleration is directly proportional to the net force and inversely proportional to the mass of the object. So I gave you the three things that are important here. F net, or net force, your acceleration, and your mass. So let's just go over these three things carefully. So make sure we know what these three terms mean. So your net force, we're going to say, is the sum of all the forces acting. Okay. Now remember that you need to take into account here if they're acting in the same dimension, in other words, up and down or left and right. Okay, so, but it's the sum of all the forces acting on the object. Okay, then we had mass, which we're going to call the amount of matter. That an object contains, okay, or an object is made up of. And what is important here is the units. And I forgot the unit for force. So for mass, our unit is in kilograms. For force, our unit is newtons, named after Sir Isaac Newton for all the work that he did on forces. And the last one is acceleration. And this is our rate of change of velocity. And from grade 10, you should remember that the unit is meters per second squared. And just to add to that, you should remember that acceleration is change in velocity over change in time. So that means that the object is going to speed up by the same amount every second. Okay, so it's nice to know what these things mean, but how do they come together? And they come together in this little equation. F net equals mass times acceleration. So the net force is equal to the product of the mass and the acceleration. And this is where you can see, if you look at those two there, mass times acceleration, hopefully your maths brain is working. Now you can see why we say that the net force is directly proportional to the acceleration. Okay, you might see this sometimes, directly proportional to the acceleration, and that your net force is proportional to the inverse of mass. So what do these two concepts mean? It means this: the greater the force, the more the acceleration is going to be. Okay, so the harder you push or the harder you pull, whatever the force is, the bigger that it is, the bigger the acceleration is going to be that the object experiences. If you push gently or you pull gently or it's a tiny little force, the acceleration is going to be tiny. At the same time, the mass of the object is not going to have the same direct relationship. What it means is, as the mass of the object gets bigger, the force that is required or the force that is experienced will get smaller. So if the force is big, the acceleration is going to be big, But if the mass is big, then the force should be small. So those are two separate things, but Newton put them together, and he said mass times acceleration is going to give us the force, and the two different experiences, one being big or one being small, or both being big or both being small, he put those two ideas together, and that's where we get the idea of net force from. And the net force that is greater than 0 is going to give us an acceleration. Okay, so it might sound like a whole lot of words. You're not too sure what this means at the moment. In the next lesson that we do on Newton's second law, it will make a lot more sense because we're going to use examples. We're going to use numbers. Okay, so if you're not sure right now, just make a little star next to it, and you need to pay attention. You need to go look things up. We will do it again. It will make a lot more sense. So as long as you know that F equals m times A, we'll leave it at that for now, and we will get into the detail next time I see you. So let's carry on to Newton's third law. Okay, so let's have a look here. We're back to our plant on the table. The cloth on the table still. The question is, what would Newton say? So Newton said this in his third law. If body A exerts a force on body B, then body B will exert a force on body A that is equal in magnitude but opposite in direction. I want to look at this word magnitude. Okay, here we can say size instead. Okay, so let's quickly break this down. According to Newton's third law, you've got to have two bodies. You've got to have body A and you're going to have body B. And it doesn't matter what they are. So this could be a man and a chair. And it could be a table and the ground. It doesn't matter what the objects are. It just is looking at how two objects relate. So now let's look at our plant on our table. Okay. What we've got here is known as an action-reaction pair, or just reaction pairs. And what it is a force diagram that shows the forces that each object is experiencing. So on the left here, the objects are the plant and the table. So what have we got here? The top one is the table. It's the force of the table pushing the plant. And what we've got at the bottom is the force of the plant pushing the table. Okay, so we've got two different objects, and we've broken and we've separated them. So what is the plant doing? What is the table doing? So what I'm going to do, because this looks a little bit messy, I've just left it as the force of the table and the force of the plant. But we have another thing to think about here. What is causing the plant to sit on the table? And that is gravity. So in other words, it is the earth pulling the plant. So you can see here that this is going to be the force of the plant on the earth, and this here is the force of the earth on the plant. And what we've got is the common factor of plant in both of them. Okay, so I know that the earth pulls down. But we're looking at what each one is experiencing. Okay, so because of the earth, the plant is pushing down. And because the plant is pushing down, the actual earth is pushing up again. So we will spend some more time on these things because these diagrams do get quite confusing. Okay, but remember, it is all about body A exerting a force on body B. and body B exerting a force on body A. So if I look at my diagram again, hopefully you notice something about the size of the arrows. What do you notice about the size of the arrows? The size of the arrows are the same. They are the same size. And what did I say the word magnitude means? Magnitude means size. Okay, so when we are drawing these Newton 3 diagrams, we have to have our arrows that indicate our forces. They need to be the same size. The whole thing about Newton 3 is that the magnitude is the same, number one, and number two, they're acting on different objects. The plant is acting on the table is acting on the plant. So our force diagrams up to now has been one object and all of the forces acting on that one object. Now we've got two separate objects and we're looking at the forces that are acting on each individual object when the two of them relate. Okay, I know it sounds a little bit confusing right now. What I want you to think about is what is happening as you are sitting down right now. I'm sitting on a chair, but I haven't fallen through the chair. You're sitting on a chair, or you're sitting on the desk, or you're sitting on the ground, wherever it is that you're sitting, you are not going through that object. So you are exerting a certain force on your chair. You're pushing down because the earth is pulling you down. But what is the chair doing to you? The chair is pushing you up with the same amount of force that you are pushing down with. Okay, so you're pushing down with a certain amount of force, the same number. So the same magnitude, the same size force, the chair is pushing you up with the same size force. Okay, that is called an action-reaction pair. You pushing down on the chair pushing up on you. That is Newton 3 or Newton's third law in a nutshell. So I want you to just think about that. Keep that in the back of your mind, because when we come back to Newton's laws in the next few lessons, I'm going to be asking you some questions about Newton 3. So just think about it. If you're not too sure, see if you can work it out. Ask a few friends, chat to people, chat to your teacher, maybe ask some of the matrics if they know what's going on. If you're not 100% sure, otherwise keep your question in your mind and hopefully we'll cover it in the next lesson. Okay, but let's move on and see what we've got as a summary, because we've done a lot of theory today, so lots to get your head around. So let's see if we can summarize these for you nicely. You need to know, by the way, just quickly, you need to know and you need to be able to quote or to rewrite all Newton's laws. At the moment, we've done 3, Newton 1, Newton 2, Newton 3. We will do law of universal gravitation, but you do need to be able to write them out and write them out properly. Okay, in your exam, your teacher can ask you, state Newton's first law or state Newton's third law, and you can't make up your own thing. You've got to write it as it's been given to you. So please make sure that you do memorize these, that you do remember them. Okay, so that you write them and you can get those marks, really nice level 1 questions. And then you know that you've got some marks in the bag, and the rest of your tests and exams should be easier for you to answer. So make sure you know your theory. Okay, so let's look at the theory, and then underneath you'll see that I've got how I understand it. The theory part you need to know, and then the understanding part is how we're going to apply it. So let's have a look at what I've got. So this part here is the part that you need to memorize and you need to be able to write down. That a body will remain at rest or continue to move in a straight line at constant velocity unless it experiences an external force. Let me just take that out there. I think I got a bit excited when I was typing. What does that mean? Object is going to stay at constant velocity. So here, V equals U. So in other words, initial velocity and final velocity is the same. Okay, so down here, we've got constant velocity. And remember, if you've got a constant velocity, what does that mean? It means that we have a 0 acceleration. We are not speeding up. And if we have a 0 acceleration, we then have a zero net force. Okay, now remember, this applies to constant velocity or it applies to zero movements, in other words, standing still. Okay, so what I've got here is how we understand Newton 1, so I'm going to call this our understanding. But here, this is what you need to be able to quote. In other words, you need to memorize and remember that to give it to your teacher. So at the bottom is how we understand it, and the words at the top where I've said quote is what you need to memorize for your exam. Okay, so Newton 2. Newton's second law, net force causes a body to accelerate in the same direction as the net force. Acceleration is directly proportional to the net force and inversely proportional to the mass of the object. Exactly like I showed you earlier on, F net is equal to mass times acceleration. Okay, so remember, this is our understanding part. That is how we understand it. And the square bracket is what we need to be able to write or to be able to memorize and quote. Okay, then Newton's third law. If body A exerts a force on body B, then body B exerts a force on body A that is equal in magnitude. Remember we said magnitude was size, but opposite in direction. So again, what we need to memorize or quote. And what do we have down here at the bottom? Its magnitude. So in other words, the size of force A must equal the size of force B. The difference is one is in that direction and the other one is in the opposite direction. Okay, so the size is the same, but the directions are opposite. One last thing. Just want to look at Newton's first law. You need to know what this is. Okay, people think this is a force. It's not a force. It is a property of material. Okay, so what inertia is that it's a resistance to movement. So in other words, if an object does not want to move, it has something called inertia. And you will see if you look in your textbook or if you go and look up other books or if you are able to go onto the internet, you will see inertia is often mentioned with Newton's first law, and it just means that an object is going to want to resist movement. Okay, guys and girls, you've done really well today. We've done a lot of theory. Thank you for working so hard. Look forward to seeing you in the next lesson.